In this video, we're going to learn the squeeze theorem for sequences and the absolute value theorem for sequences. Once we go over the theorems and what they say and what they mean, we'll apply them to a couple of sequences to determine whether those sequences converge or diverge. So here's the theorem. Let's say you have three sequences, and they're represented by A sub n, B sub n, and C sub n. Let's say that A sub n, the sequence we're interested in, has values that are in between the values of B sub n and C sub n for all n greater than some particular n. I'm going to use capital N for that particular n. Well then, if B sub n and C sub n are both convergent and they converge to the same number, then since A sub n is squeezed in between them, that sequence A sub n converges to that number as well. So let's look at some pictures. This is a natural generalization of the squeeze theorem that you learned in Calculus 1. In Calculus 1, though, we were evaluating a limit as x approached a particular value. Here we're letting n go to infinity whenever we're talking about convergence of sequences. So let's say that this is the line y equals L. And A sub n, or B sub n and C sub n both approach L as n goes to infinity. So maybe the terms of B sub n look like this. So B sub n kind of has this behavior. So that green sequence represents B sub n. That's the smallest one on this list. And then C sub n might be up here. And it's okay if that inequality doesn't hold for all n, but maybe after a particular n, maybe n equals 3, that inequality holds. Then, if our sequence A sub n lies in between these two guys for n greater than some n, maybe it's n equals 3. I'm going to use the big black dots to represent the sequence A sub n. Well, if the blue sequence is approaching L and the green sequence is approaching L, and this black sequence, the one represented by the black dots, is squeezed in between them, well then I think it makes sense that if this guy is going to L and this guy is going to L, and A sub n is squeezed in between them, then A sub n has to go to L as well. And all of these are as n goes to infinity by the squeeze theorem. One way that I recommend that you notate this is if you have that inequality with three parts, provided all three limits exist, you can take the limit of each of those parts and those inequalities will hold. So we'll say the limit as n goes to infinity of B sub n is less than or equal to the limit as n goes to infinity of A sub n, which is less than or equal to the limit as n goes to infinity of C sub n. Now, the theorem says we're assuming that B sub n and C sub n both approach L. So L is less than or equal to the limit as n goes to infinity of a sub n, which is also less than or equal to L on this side. So this limit is greater than L or equal to L, and it's less than L or equal to L. The only way it could, well, the only value it could possibly be to be less than or equal to L and simultaneously greater than or equal to L is L. So that's what the squeeze theorem says. If a sub n is squeezed in between these two sequences and these guys go to L, the guy in the middle has to go to L too. L as well. Okay, so here is a sequence where I might use the squeeze theorem to show that it converges. Now it's not 100% obvious that the squeeze theorem applies here. In order to use the squeeze theorem, I need a sequence on the left and the right, or graphically it's going to be like below and above the terms of the sequence that I'm looking at, the sequence a sub n equals sine of n over n squared. But there are like built-in comparisons. Every time you see a sine of n or a cosine of n, you know from trig that if I graph a sine graph, if I graph y equals sine of x, it looks like this. You know from trig that the values of sine of x, the y values, are all between -1 and 1, and it just keeps repeating. You go from 0 to 1 to 0 to -1 to 0 to 1 to 0 to -1, and it just keeps going, right? So all those y values are between -1 and 1. The same is true for cosine. Now cosine starts at its max, and then it has this behavior. And all of these values are between -1 and 1. So we start at 1, we go to 0, then we go to a min of -1, then back to 0, then up to 1. So it goes 1, 0, -1, 0, 1. That's cosine. But you see all of the outputs, all of the y values or the range values for these two graphs are all between -1 and 1. I can use that fact here. Now given that this is true, when I plug in an integer n, sine of 1, sine of 2, sine of 3, those are just going to be points on this graph. Now they're not guaranteed to be at mins or maxes or anything like that because these are radians. These special things are happening on our sine function at 1/4 of the period, and our period is 2 pi. So that's pi over 2. That's about approximately, very roughly, 3.14 over 2. So it's about 3 over 2, about 1.5. So sine of 1 is somewhere over here. And then sine of 2, well, it's somewhere in between 1.5 and 3. So it's going to be on this interval. And sine of 3, well, that's actually going to be a little bit before pi. So we're going to have 3 little dots on here for sine of n. And we would keep going. So sine of n doesn't lie on any special points on this graph, but they are on the graph at all the integers. So we'll have sine of 1, maybe sine of 2, maybe sine of 3, something like that. Sine of 4 is on the other side, and so on. Okay, so I can use the fact that the range is -1 to 1 to write down an inequality. So sine of n is always going to lie between -1 and 1, and it won't be equal to -1 or 1 because n is never going to be one of these special values, an odd multiple of pi over 2, because n is an integer. So this is true for all n. All n in the natural numbers. This little, it looks like an E, it's an epsilon. This means n is in this set. And this set is the set of natural numbers. So that is the set of counting numbers, starting with 1, 2, 3, 4, and so on. Okay, so I have this inequality, and this is a very good place to start because look at this, the form of the squeeze theorem. I've got to have the terms of the sequence I'm interested in between two other sequences. Well, because that numerator was sine of n, I can immediately write this down, which is nice. Now looking at this, I need to have the sequence that I'm interested in the middle here. So I need this to be a sine of n over n squared. I can make it sine of n over n squared if I divide all three parts of this inequality by n squared. So I'll divide this by n squared, and divide this by n squared, and divide that by n squared. Okay, now I've got my comparison functions, or my comparison sequences. Now, if this function and this function converge to the same thing, then by the squeeze theorem, I can conclude that this one converges to the same thing. Now, if this one converges to 3 and this one converges to 4, that tells me nothing about this one in between. This one may or may not converge, and if it does converge, it might converge to any number between 3 and 4 at that point. So let's assume all three limits exist. So we're assuming these three sequences converge. If they don't converge, the following inequality is not true. But if they do converge, the following is satisfied. I can take the limit of all three parts here. The limit as n goes to infinity of negative 1 over n squared has to be strictly less than the limit as n goes to infinity of sine of n over n squared, which is less than the limit as n goes to infinity of 1 over n squared. Now, the original inequality dealt with particular values of n from the natural numbers, and we said that sine of n was between negative 1 and 1, and that's absolutely true. But in the limit, it's possible that we might add an extra value here. So I'm going to change this less than and this less than to less than or equal to and less than or equal to. Because limits are kind of funny. Whenever things go to infinity, things behave slightly differently. So I'm going to add that here. If you're curious about that, if you're saying, Miss Townsend, I'm dying to know why you put a less than or equal to sign rather than a less than sign, send me a text and we can talk about it. So provided these three limits exist, this inequality is true. Now let's take the limit of this one and see if we can find the limit of this one in between. As n goes to infinity, this is negative 1 over a very large number squared, so this is 0. And over here, as n goes to infinity, this is positive 1 over a very large number squared, so this is 0. So this guy is squeezed in between a 0 and a 0, so it's simultaneously greater than or equal to 0 and less than or equal to 0. The only way that happens is if the limit of the function in between is 0. And I'm going to write by the squeeze theorem. Some people call that the sandwich theorem. Some textbooks do. That just makes me hungry. I like the squeeze theorem better. So I imagine that visually squeezing one function in between two other functions. Now, the question usually asks, does this sequence converge or diverge? And we can say yes, the limit is finite. So the sequence given by s sub n over n squared converges to 0 by the squeeze theorem. So that's our first theorem. All right, let's do another example using the squeeze theorem. This one is a classic example. It's in our textbook, but I wanted to go through it with you as well. We're trying to determine whether the sequence given by 1 over n factorial is convergent or divergent. And here I want to do something very similar to what we just did with the sine of n, or the sine of n over n squared problem. I want to find an inequality that I can compare this to. A couple of functions on the left and the right that I can compare this to. One way that we can do this is we can expand this n factorial and compare it to an exponential function. So let's say I've got n factorial over here. So that's 1 times 2 times 3 times 4 times 5, and we keep going until we get n minus 2 times n minus 1 times n, and we stop. Because n factorial, you start with n and you multiply down. 1 less, 1 less, 1 less, and then eventually get to 3 times 2 times 1. Okay, I want to compare this to powers of 2. Well, I'm going to leave that 1 alone. I'm going to compare that 2 to another 2. And that 3 is definitely greater than a 2 over here. And that 4 is definitely greater than a 2 over here. So eventually I'm going to have 2 times 2 times 2. And what I'm doing is I'm comparing each of these 2's on this side to each of the numbers on this side. That 2 and that 2 are equal to each other. This 3 is greater than that 2. So I'm going to put a greater than sign. That 4 is greater than that 2. This n minus 2, if n is large enough so that this actually makes sense, if n was 10, this would be 10, 9, 8. 8 is going to be greater than that 2. As long as n is greater than 4, this is greater than that 2. And as long as n is greater than 3, or greater than or equal to 3, well, strictly greater than 3, this n minus 1 is greater than that 2, and then this n is going to be greater than that 2. So this n factorial on this side is greater than this. This is powers of 2. How many 2's are over here? Well, I had 1 2 for all of these guys. I didn't have a 2 for the 1. So there are n factors on this side. If this was 10 factorial, I'm going to have 1 times 2 times 3 times 4 times 5 times 6 times 7 times 8 times 9 times 10. So there would be 10 of them. In general, there's going to be n of them. Over here, I'm going to have 1 less because I'm not taking care of that 1. I'm comparing all of these 2's to those 9 factors over here. So this is strictly greater than 2 to the n minus 1. And I think that we can see that. I think that that makes perfect sense because this 3, the 4, the 5, like all of these numbers by design are greater than those 2's. Now think about how exponential functions work. I'm taking a 2 and I'm doubling it, so I get another 2, and then I'm doubling it and I get another 2, and I'm doubling it. And every time I multiply by 2, I'm just doubling the last answer. Well, this is saying something different. This one doesn't say double it, don't multiply by another 2, now multiply by 3, and then multiply by 4, and then multiply by 5. So we're continuing to multiply, but we're multiplying by something greater than that 2. So this is definitely larger than this. And, well, both of these, provided that n is greater than or equal to 1. So if this was n equals 1, we'd get 2 to the 0, which is 1. Well, actually, it doesn't matter what n is. For both of these sides to make sense, n has to be 0 factorial or more. Would you guys agree that no matter what n is, that's going to be positive? I hope so. I'm just multiplying a bunch of positive numbers together. And then I'm multiplying, if I've got n factors over here, I've got n minus 1 factors over here. I'm multiplying that many 2's together. So this is greater than this, which is greater than 0. Ooh, do I want to do that? Do I want to compare it to 0? I don't know if that's going to work. Maybe I don't want to compare it to 0. That was a bad idea. I was thinking of something else. Okay, so I've got n factorial is greater than this. All right, now I want to do something that's going to seem a little odd, but it'll make sense later, I think. If I have 2, or if I have 3, and I know that 3 is greater than 2, if I take reciprocals of that, if I'm comparing 1/3 to 1/2, don't I have to flip that inequality? Because if 3 is greater than 2, and I take 1 and I divide it into 3 even pieces, well, thirds, 1 divided into 3 even pieces, each of those pieces is going to be smaller than if I took 1 and I divided it into 2 equal size pieces. So, yeah, if I'm taking 1 and I'm dividing it into more pieces, that fraction is smaller. So if the denominator is larger, the fraction is smaller, provided that the numerators are the same. If the denominator is smaller, the fraction is larger, provided that the numerators are the same. Because I'm taking one number and I'm dividing it into either more pieces, making it smaller, or less pieces, making it larger. With that in mind, let's take the reciprocals of these guys. If this is larger than this, when I flip it, when I take reciprocals on both sides, 1 over n factorial, which is my a sub n, has to be less than this. So I've got a larger denominator here, so it's going to be a smaller fraction. Okay, now I plan to use the squeeze theorem. Problem is I don't have anything else to compare this to. I tried to compare to 0 over here. That was a bad idea. This is what I want to do instead. This I know is positive, right? Because n factorial is always positive. So if this is positive and this is positive, I can say both of these are greater than 0. This is for all n, for which these are well defined. So let's just say for n equals 0, 1, 2, and so on. Well, if n equals 0, we could have a less than or equal to sign. There we go. Okay, now by the squeeze theorem, if the limit of this sequence of zeros exists and the limit of this sequence exists, then the limit of this sequence exists, and it has to be the same as the limit of these two guys. So let's assume that all three limits exist. And we'll take the limit of each part of this inequality. So I've got the limit as n goes to infinity of 0 is less than the limit as n goes to infinity of 1 over n factorial, which is less than the limit as n goes to infinity of 1 over 2 to the n minus 1. And I'm going to put less than or equal to signs because things get a little different when we add infinity. Infinitely many numbers, they can approach these limiting values, which might make that less than into a less than or equal to. Well, we know that this sequence of 0, 0, 0, 0, it's pretty boring. The limit's clearly going to be 0. And provided this limit exists, this limit has to be less than this limit. And as n goes to infinity, 2 to a large power is going to be a large number. 1 over a large number is a small number. And as n gets larger and larger, this fraction gets smaller and smaller, so we get 0. So the limit of the sequence we're interested in is greater than 0. And it's also it's greater than or equal to 0. It's also less than or equal to 0. The only way it could possibly be greater than or equal to 0 and less than or equal to 0 at the same time is as if the limit equals 0. So we can say the limit as n goes to infinity of 1 over n factorial is 0 by the squeeze theorem, because it's squeezed in between those two zeros. Okay. Now the next theorem I want to talk about is called the absolute value theorem. This is another one that makes intuitive sense to me. It says, if the limit as n goes to infinity of the absolute value of a sub n is 0, then it so happens that the limit as n goes to infinity of a sub n would have to be 0 as well. And I think that makes sense because of what we know about absolute value. If I'm comparing a sub n to its absolute value, aren't those always going to be, well, if a sub n is positive, those are going to be the same, right? So I could put an equal sign. But if a sub n is negative, the absolute value is clearly larger because it's the positive version of that. So a sub n will always be less than or equal to the absolute value of a sub n. And it's also always less than or equal to the negative absolute value of a sub n. Let's think about why that might be true. Well, if a sub n is negative, its absolute value is positive. And so if I multiply a positive by a negative, this is a negative number is less than or equal to this negative number, and they're going to have the same magnitude, same absolute value, so this is true. Now, if a sub n is positive, well, then the negative absolute value is a negative number, and a sub n is positive, so this inequality is also true. So if this is true, and I know that the limit as a sub n, or the limit of the absolute value of a sub n as n goes to infinity is 0, provided all three limits exist, and these guys do, this one is squeezed in between. So by the squeeze theorem, when I take the limit as n goes to infinity of this side, and the limit of my middle sequence, and the limit of that larger sequence, graphically it's going to be the top sequence, the one that's above the other two sequences. If this guy goes to 0, and this guy goes to 0, and this limit is simultaneously greater than or equal to 0 and less than or equal to 0, then this limit has to be 0 as well. Okay, so that's true. Keeping that in mind, let's look at this one. Well, I've got b sub n here, and I want to know whether this sequence converges or diverges. I notice it has a negative 1 to the n in it. That's going to make this sign alternate. When n is 1, it's going to be a negative 1 in the numerator. When n is 2, it's going to be a positive 2. Let's just write out a few terms to this sequence so that we can get a sense of what's going on. So we have b sub 1, b sub 2, b sub 3, b sub 4, and so on. Eventually we're going to have a b sub n, and we're going to keep going forever. That's our infinite sequence. B sub 1 is negative 1 to the first over 1 squared plus 3. So that's negative 1 over 4. B sub 2 is negative 1 squared over 2 squared plus 3. I'm just replacing the n with a 2, so it's negative 1 squared, 2 squared plus 3. It's positive 1 over 7. B sub 3 is negative 1 cubed over 3 squared plus 3. So that's negative 1 cubed is negative 1. 3 times 3 is 9. 9 plus 3 is 12. And so on. So I'm not going to write them all out, but I get negative 1 over 4, 1 over 7, negative 1 over 12. And we keep going, and eventually b sub n is negative 1 to the n over n cubed, or n squared plus 3. And we keep going. Run out of space a little bit. It looks like they're alternating. When n is 1, we get negative 1/4. When n is 2, we get 1/7. That's 1 divided into 7 pieces. Oops, I wrote it on the wrong side, didn't I? Negative 1/4 is going to be down here. Now 1 over 7 is 1 divided into 7 pieces. Those pieces are going to be smaller than if I took 1 and I divided it into 4 pieces. So 1 over 7 is here. We have that. Negative 1 over 12. I took 1 divided into 12 pieces. These pieces are smaller, but then I make them negative because I've multiplied by a negative 1. I hope you see what's happening. The magnitude of these, the absolute value is getting closer to 0, but we're going on either side of the line. I'm not going to draw it with tick marks because it's hard to draw, but what we see is something that looks like this, like if we keep going. We're going back and forth on this line, but when the terms are even, they're approaching 0. When the terms are odd, they're approaching 0. And I think in general they're approaching 0. Now that's not a proof. We're going to use our theorem to prove it. This theorem is based on the squeeze theorem, and we know it to be true. So I've got this negative 1 to the n, which is alternating. I'd like to get rid of the alternating part, so I'm going to take the absolute value and then use the absolute value theorem. So I'll take the limit as n goes to infinity of the absolute value of b sub n. I'm just using b sub n this time so that we can mix it up, have a different letter instead of a sub n. Not all sequences are named a sub n. Not all functions are named f. Alright, so we're here, and as n goes to infinity, this is a large number squared plus 3. So I get a large number. 1 over a large number is a small number. So I get 0. What does that tell me? According to the theorem, if the limit as n goes to infinity of the absolute value of b sub n is 0, well then the limit as n goes to infinity of b sub n is 0. That's what the theorem says. And it's consistent with our picture. If half the time it's approaching 0 from above, the other half the time it's approaching 0 from below, in general it's approaching 0. So we have the limit as n goes to infinity of b sub n is 0 in that case. Alright, and I think that's it for this video. So we've talked about the absolute value theorem, which is right here. We've also talked about the squeeze theorem and done a couple of examples. In the next video, we'll talk about monotonic sequences, bounded sequences, and the bounded monotonic sequence theorem.